Hi, this is Mr. Cutchell, and today we're going to talk about the ideal gas law. Now, this gas law is different than the other gas laws insofar up to this point we've studied things that have pressure, that have volume, that have temperature in them, but we haven't looked at the number of moles, and that does change some of the factors. So, for example, you can see this little kid over here blowing up a balloon. As he puts more molecules into the balloon, the volume increases. In other words, the more moles that he adds into the balloon, the greater the volume. So now we're going to take into account the number of moles as well. So we're going to look at the ideal gas law when we have pressure, volume, temperature, and the number of moles. To do this, we're going to have to look at something called the ideal gas law constant, which is the value of R here. So let's go ahead and take a quick review of Avogadro's hypotheses. So let's go back and revisit Avogadro's hypothesis. Now, Amedeo Avogadro said that equal volumes of all gases, if the temperatures and pressures are the same, contain an equal number of moles, in other words, the same amount of gas. So let's take a look at two balloons that have equal volumes. If they're in a room in which they have equal volumes, then what's the same? Well, what's the same is the following. We know that temperature is going to be the same because the outside temperature is the same. The pressure is going to be the same, the volumes are going to be the same, and therefore they're going to have an equal number of moles. So N, which is the number of moles, is going to be the same. So the number of moles here is going to equal the number of moles here because these volumes are the same. We're interested in one particular application of this, and that's STP conditions. So if you remember, STP is standard temperature, and that's 0 degrees Celsius or 273 Kelvin. And standard pressure is 1 atmosphere, which is 101.3 kilopascals, which is 1 atmosphere, and so on. So for example, if we look at this picture here, this is a picture in which we have ice and water, and the ice here we're going to say is at 0 degrees Celsius or 273 Kelvin, and that would be standard temperature. At sea level, on a day when it's 0 degrees Celsius out, the standard pressure is 1 atmosphere, or we could say that's 760 millimeters of mercury, or 101.3 kilopascals, and so on. So when we have standard temperature and standard pressure, what do we know about the volume of 1 mole of gas? Well, 1 mole of gas at STP conditions is going to occupy 22.4 liters of space. And that's going to be important as we go on to our next slide. So let's use STP to determine the value of R for our ideal gas law equation, which is PV equals nRT. In order to figure out what R is, we need to know what P, V, N, and T is. Well, we know the standard temperature is 273 Kelvin, so we've got temperature. Standard pressure, we're going to use kilopascals, is 101.3 kilopascals. So we know that. The volume is 22.4 liters if we have 1 mole of gas. So we've got everything here except for R. So if we have PV equals nRT, then PV divided by N times T is going to equal R. So let's go ahead and calculate this. By the way, this should be R down here. R, right here, the value for R is going to equal PV divided by N times T. We'll plug our values in. 101.3 kilopascals on top, 22.4 liters on top, divided by 1 mole on the bottom times 273 Kelvin. And we're going to get a very important value here. This is the value for R. It's called the ideal gas law constant. It's called the ideal gas law constant, and it's basically R. So 8.31 kilopascals times liters per atmospheres per mole. Now, we can have many different values for R. All depends upon what units we're using. If we have atmospheres here, or inches of mercury, or kilopascals, or millimeters of mercury over here, our value for R will change depending upon if we use liters or meters cubed and so on. So if you look here, there's actually 70 different values we could memorize, which is way too much. So we just used one value. And so don't memorize all 70 of the values for R. Know the value for R using kPa. And we know that that's going to be 8.31, and that's going to have a units of liters times kilopascals per mole times kelvins. We use that and know the value for R using kPa, and then convert all your pressures in your problem to kilopascals using your pressure conversion guide. So let's go ahead and take a look at an example of this. Here's a problem in which we have dinitrogen monoxide, it's laughing gas. Says we have 2.86 moles of the gas and it occupies 20-liter tank at 23 degrees Celsius. What is the pressure in millimeters mercury in the tank in the dentist's office? Okay, so what do we know? We know that we have N, which is 2.86 moles, and we know that it occupies a volume of 20 liters. And we know the temperature is 23 degrees Celsius, but of course we have to add right away 273 to that to get this into Kelvin, so that will be 296 Kelvin. And then it's asking us for the pressure in millimeters mercury. So we'll go ahead and figure out what the pressure is in kilopascals first, and then we'll eventually change that to millimeters mercury. The value for R, we know, is 8.31 liters times kilopascals per mole times Kelvin. Okay, so now we want to go ahead and use the ideal gas law to solve this problem. So we're going to use PV equals nRT. We want to solve this for pressure. We want to get pressure by itself. So we'll divide this side by V, divide this side by V. This V over here cancels, so pressure is going to equal N times R times T over V. Well, N is the number of moles, so we're going to plug in 2.86 moles times the value of R, which is 8.31 kiloliter, or okay, so let's take a look at this problem. In this problem, we're going to try to identify the variables, and as we can see, the first thing they tell us is that we have dinitrogen monoxide, and the amount of moles is 2.86. So on the left-hand side, I wrote down N equals 2.86. N stands for the number of moles. We also know the volume is 20 liters. The temperature is given to us in 23 degrees Celsius, but we have to add 273 to get it into Kelvin, so it's 296 Kelvin. What is the pressure in millimeters mercury? So we go pressure equals question millimeters mercury. And then the value for R, we know one value for R, it's 8.31 liters times kilopascals per mole Kelvin. So let's go ahead and try to solve this problem for P. So what we'll do is we're going to go ahead and write out the ideal gas law over here. PV equals nRT. We'll solve this for pressure by dividing both sides by volume. And when I do that, my volumes are going to cancel out. So now I can plug in my numbers for nRT over V. I'm going to get, my pressure will be N, which is 2.86 moles, times the value for R, which is 8.31 liters times kilopascals per mole Kelvin. And my temperature is 296 Kelvin, all divided by the volume. The volume in this case is 20 liters. So now when I start to cancel these units out, I'm going to get moles canceling with moles, kelvins with kelvins, liters with liters. I'll be left with kilopascals. When I multiply all of this out, I'm going to end up with a value of 351.75 kilopascals. which is a pressure, but we have to convert that kilopascals to what they're asking for, millimeters mercury. So I'm going to use my pressure conversion guide to multiply by 760 millimeters mercury for every 101.3 kilopascals. And when I do that, the units of kilopascals are going to cancel out. And the math tells me here I'm going to get a final value of 2,638.9 millimeters mercury. Or that's basically, when you take into account significant digits, 2,640 millimeters mercury. So that's how you use the ideal gas law to solve problems. Let's take a look at a problem from your packet. This problem number 54 in your packet, if you go ahead and find this, let's go ahead and look through this real quick. What would be the temperature? So we're trying to find the temperature, T equals question mark, of 32 grams, so that's the mass is 32 grams of NO2. So the very first thing I'm going to do is change that to moles. So to change mass to moles, we take 32 grams times 1 mole over the molar mass, so it's 1 mole. The molar mass of nitrogen dioxide, nitrogen's 14, each oxygen 16, that's going to be 46 grams. And that's going to give me 0.696 moles. Okay, and then it says the volume is 45.9 liters. And we have a pressure here in atmospheres. So this pressure is 3.12 atmospheres. Of course, we're going to want to change that right away to kilopascals. That's going to be our value for R. So we'll multiply by 101.3 kilopascals for every 1 atmosphere. I get that from my pressure conversion guide. When I multiply that together, I'm going to get 316.056. We'll just round it out to 316 kilopascals. So now when I use my value for R, we know R is going to be 8.31 liters times kilopascals per mole times Kelvin. So now I can use the ideal gas law. PV equals nRT. We try to solve this for T, so I divide both sides by nR. Divide this side by n times R. N cancels, R cancels. We can now plug in. So I take my pressure, 316 kilopascals, times my volume, which is 45.9 liters, all divided by N, which is going to be 0.696 moles, times my value for R, which is 8.31 liters times kilopascals per mole times Kelvin. Now I can just double check this to make sure that the liters cancels with liters, kilopascals with kilopascals, moles with moles. We're going to end up with Kelvin as our final value. When you multiply this out, be sure to take everything on top in parentheses, divided by everything in the bottom on parentheses. And when you do that, you get a final value of 2,508 Kelvin. So that's your final answer for this problem. Well, that's about it. The remaining time today, if you could work on the problems 46 through 55 in your packet. They're all ideal gas law problems. Show all your work as you're going through, and good luck.